Hi guys, I welcome you to my YouTube channel, Learn Physics with IBM. That is my contact. And today I gathered the courage to take you to another episode of Learning Physics that is going to be solved past paper questions. Not forget, this is AS Physics multiple choice questions. We are dealing with kinematics and dynamics. I record these multiple choice questions in one together because it is very hard to draw a boundary between kinematics and dynamics in multiple choice questions. Even in structured questions, there is a lot of overlap. So this is part 12, and I would like to, without wasting time, to take you to the document so that we solve questions for part 12. So without wasting time, in part 11, I think we stopped here, and we said our answer into this question was A rather than C, because they say the mass or the body comes to rest along xy somewhere here. That means it does not rapidly go to rest. That means the velocity does not rapidly go to zero. So that's why we could choose A rather than C, because C shows it almost. C was showing that almost comes to rest in a very short period of time. It almost comes to rest very close to Y, very rapidly to. It takes a very shorter period of time to come to rest. Yet it comes to rest along X and Y. So or between between Y and X. So it may take a longer period of time to rapidly go. I mean to decelerate to zero. So that means the answer is A. So in part 12. A body experiences a varying resultant force that causes its momentum to vary as shown in the graph. At which point does the resultant force have the largest value? So we know by definition of force is equal to the rate of change of momentum. And of course, from a graph of momentum against time, force is going to be equal to the gradient. Force is going to be the gradient. So we want a point where the resultant force is the largest. So we just look for the greatest gradient. So the greatest gradient is going to be at B, because the graph is steeper at point B. At A, the gradient is almost zero. At C, the gradient is almost zero. When we compare D and B, we notice that B is steeper than D. So where the gradient is greatest, the force is greatest. So the answer is B. A golf ball of mass m is dropped onto a hard surface from a height h1 and rebounds to a height h2. The momentum of the golf ball just as it reaches the surface is different from its momentum just as it leaves the surface. What is the total change in the momentum of the golf ball between these two instants? Ignore air resistance. If we are ignoring air resistance, then the acceleration due to gravity is going to be constant. So I'll begin with the first case when it just falls. Loss in kinetic energy. The loss in because it is falling, it is dropped onto a hard surface. So the gain in kinetic energy or loss in gravitational potential energy is equal to the gain in kinetic energy when it falls. So for the first case, I'll have that I have m velocity v1 squared should be equal to mg h1 for the first case. If I make v1 the subject, it means v1 is going to be equal to the square root of twice g h1, since m cancels out. So that means if I find the initial momentum before it hits the surface, momentum m1 is going to be m times v1, which is going to be m times the square root of 2g h1 for the first case. When it rebounds, it loses kinetic energy as it gains potential energy. So again, I'll say I have the loss in kinetic energy, which is I have m, its velocity is v2 squared, is going to be the gain in potential energy, which is mg, the height to which it raises h2. So if I make V2 the subject, V2 is going to be equal to, again, the square root of twice 2GH H2. So that means the momentum P2 in this case, but remember in the opposite direction, is going to be M square root of twice GH1. So downward, if downwards is positive momentum, then upwards is going to be negative momentum. So we want total change in momentum. So the change in momentum is going to be equal to P minus P1 minus P2. But remember, P2 is negative, P1 is positive. So this is going to be M root of 2GH1 minus negative, which becomes plus M root of 2GH2. So that means our answer is automatically going to be B. The diagram shows a particle X with kinetic energy Ek about to collide with a stationary particle Y. Both particles have the same mass. After the collision, X and Y travel onwards together as a single larger particle. So they move with a common velocity. How much kinetic energy is lost in the collision? So let's first find the velocity with which they move. Before collision, total momentum is going to be m, then the mass be m because they have the same mass. So total momentum before collision is m times the velocity of the particle x, which I'm going to call u. And after collision, total momentum is going to be, they stick together, total mass is twice m, let the velocity with which they move be v. So initial velocity u is equal to actually twice v, is twice the final velocity. Okay, so initial velocity u is equal to 2 times the final velocity. So how much kinetic energy is lost? So the loss in kinetic energy is going to be equal to E1 minus E2. Total kinetic energy before is going to be a half times m, initial velocity is u squared, which is going to be, remember u is twice v, so this is going to be, minus final kinetic energy, which is going to be a half times total mass, which is twice m, times total velocity times the final velocity, which I called v, but this is squared. Remember, u is twice v, so this is going to be equal to a half. No, let me just do it naturally so that it is easier for us to see the difference. This pen has a problem. I think I need to change the battery of this pen. Okay, so initial kinetic energy, which they called Ek. Of course, E1 is simply going to be Ek, but what is Ek? Ek is a half times the mass was m times u squared, where u is twice v. So this is a half m. 2v squared becomes 4v squared, so that is times 4v squared, which becomes just 2mv squared. That is total kinetic energy before collision. Then after collision, E2 is going to be a half times the total mass, which is twice m because they stick together. They move with the common velocity v, but squared. So this gives us mv squared. So what is the change or the loss in kinetic energy? Is going to be 2mv squared minus mv squared, which is going to simply be mv squared. That's the loss in kinetic energy. So the question was, how much kinetic energy is lost in the collision? So mv squared is a half of what we had before. So it means this is equal to a half of the initial kinetic energy Ek, because Ek was twice mv squared. So this is Ek over 2. So the answer here is going to be C. A box of weight 30 newtons is released from rest on a ramp that is at an angle 30 degrees to the horizontal. The box slides down the ramp so that it falls through a vertical distance of 80 meters. A constant friction force of 10 newtons acts on the box while it is moving. What is the kinetic energy of the box after falling through the distance? After falling through this distance. Okay, so first of all, if I make this a triangle, it will be easier for us to see that if this distance here is S and this is 80 meters, so we notice that sine theta, sine of 30 is equal to the distance. Let me use D for distance. Sine of 30 is equal to the opposite, which is 8, divided by the distance D, which means the distance D is equal to 8 divided by sine of 30. Sine of 30 is a half. 8 divided by sine 30, that is going to be 16 meters. So the distance from this point to the other point is 16 meters. This distance is 16 meters. What is the kinetic energy of the box after falling through this distance? Note that there is frictional force which acts in the opposite direction. There is frictional force acting in the opposite direction. And let me see. It is released from rest. If we ignore air resistance, we can now find the acceleration. So the resultant force down the ramp, we have a force which acts down the plane, which is going to be 30 sine of 30, that is down the plane. Then there's friction in the opposite direction, which is 10 newtons. So the resultant force by Newton's second law, resultant force is MA, which is going to be 30 sine of 30 minus 10. So that means the acceleration is going to be 30 sine 30 is going to be 15 minus 10, which is, I think 15 minus 10, that is 5 divided by the mass. So this is going to be equal to, what is the mass? We have the weight. So the mass is the weight over acceleration due to gravity, 30 divided by 9.81. Okay, so the acceleration is going to be 30 sine 30, which is 15 minus that, which is 5, divided by 30 over 9.81. So this is the acceleration, 5 divided by 30 divided by 9.81. So this is 1.635. 1.635. That is the acceleration. It is constant. I have the distance. I can use another equation of motion such as v squared equals to u squared plus 2as. So if it starts from rest, then u is 0. I have the acceleration. I have s. So I want the kinetic energy at the end. So what is v is going to be the square root of, if it started from rest, initial velocity is 0, so that is 0 squared plus 2 times the acceleration, which is 1.635 times s, which is 16, which is the distance along that ramp. So what is v? That 1 times 2 times 16, then you get the square root of the answer. So v is 7 why do I find v? Okay, v is 7.23. V is 7.23 meters per second. Then kinetic energy is going to be a half m, which mass is, of course, we have said the mass is weight, 30 divided by g, which is 9.81, then times v squared, which is 7.23 squared. I would not have got the square root. So that answer, I will square it again to take it back. Then times 30 divided by 2 times 9.81. So this is giving me kinetic energy as 80. So this is 80 joules. So the answer here is going to be A. A skydiver falls vertically from a stationary balloon. She lifts the balloon at time t equals to 0. At time t equals to t, she reaches terminal velocity. So at capital T, she reaches terminal velocity. And of course, at terminal velocity, we know that the acceleration must be 0. So she leaves the time t, skydiver falls vertically. So initial velocity is 0 in the first case. So initial velocity will be 0 at t equals to 0. And she leaves the balloon at t equals 0. At time t equals to capital T, she reaches terminal velocity. Which graph shows the variation with the t of the force? If F is due to air resistance, that means when there is no speed at t equals 0, the initial value of F should also be 0. F this time is not resultant force, so that means D is out. D is going to be out. At t equals to 0, when there is no motion, air resistance is 0, so the F starts from 0. So that means D is out. But then, at terminal velocity, when V is constant, so when V equals to constant, when V is equal to constant, the acceleration is 0. Resultant force, F resultant is going to be 0. If F resultant is equal to 0, it means the resistive force is going to be equal to the weight. Think of an object falling, the weight is downwards, and the resistive force F is upwards. So if there is no acceleration at constant velocity, it means the resultant force is also the frictional force or resistive force is equal to the weight. At that point, when we reach terminal velocity, the resistive force is equal to the weight. And remember, weight of a body is constant. And remember, W is constant. Weight of the body is constant. So it means here, F will not depend on V. So at T, F must be, at capital T, F must be equal to the weight, and of course the weight will be constant. So it means here it is showing that the resistive force is still increasing even after terminal velocity. So this is not correct. Remember, at terminal velocity, F will be equal to the weight, which is going to be constant. So also, A is going to be wrong because we know that a force due to air resistance is directly proportional to the square of the speed. So it cannot be a straight line from the origin. So it can't be a straight line. So the answer is going to be B. This one is wrong because F is directly, force due to air resistance is directly proportional to the square of the speed, which is a curve going upwards. That's why you see this part here. But then at terminal velocity, we have seen that F is going to be equal to the weight, and the weight is constant, so F remains constant at that point. So the answer is B. The diagram shows an arrangement to stop trains that are traveling too fast. Speed 50 meters per second, direction of travel, train Mach 1, Mach 2, maximum speed 10 meters per second at Mach 2. Trains coming from the left travel at a speed of 50 meters per second. At Mach 1, the driver must apply the brakes so that the train decelerates uniformly. So equations of motion can apply here because the deceleration is uniform. In order to pass Mach 2 at no more than, so the speed at Mach 2 should not exceed 10 meters per second. The train carries a detector that notes the times when the train passes each Mach and will apply an emergency brake if the time between passing Mach 1 and Mach 2 is less than 20 seconds. So the time should be 20 seconds. How far from Mach 2 should Mach 1 be placed? So that is very easy. We just need to find the acceleration. So the acceleration or the deceleration is going to be final velocity should be 10, initial should be 50, divided by 20. I think this is minus 2 meters per second squared. Then using v squared equals to u squared plus 2as. Then 10 squared should be equal to 50 squared minus 2 times 2 because of the negative 2, then times the distance which we want, which I'm calling s. So 100 minus 50 squared divided by negative 4. So I'm getting s as 600. So the distance s should be 600 meters. So they should be 600 meters apart. So the answer is D. A strong wind of speed 33 meters per second blows against a wall. The density of the air is 1.2 kilograms per meters cubed. The wall has an area of 12 meters squared at right angles to the wind velocity. The area has its speed reduced to 0. So from 33 to 0 when it hits the wall. What is the approximate force exerted by the air on the wall? So force is equal to the rate of change of momentum. So this is going to be mass change in velocity over t. But remember, mass is equal to density times volume, and volume is equal to cross-sectional area times another distance, and that distance can be speed times time. So it means the mass can be density times cross-sectional area times speed times time. So this is going to be equal to density times cross-sectional area times speed times t, then times a difference in velocity, then again divide by t. So this t cancels out. So we now substitute to find the force. This is going to be the density, which is 1.2, times cross-sectional area, which is 12, times speed, which is 33, times change in speed, which is 33 minus 0. So this gives us 1.2 times 12 times 33 times 33, which gives us 15681. 15681, or approximately 16000 newtons. So the answer is going to be D for that case. Two bodies traveling in a straight line collide in a perfectly elastic collision. Momentum is conserved, kinetic energy is conserved for perfectly elastic collision. Which of the following statements must be correct? The initial speed of one body will be the same as the final speed of the other. That is not true. The relative speed of approach between the two bodies equals their relative speed of separation. So the answer is B. That means kinetic energy is conserved. Relative speed of approach should be equal to relative speed of separation for the collision to be perfectly elastic. So the answer is B. Total momentum is conserved, but total kinetic energy will be reduced. It must be conserved also. One of the bodies will be stationary at one instant. That is not true. So the answer is B. A submarine is in equilibrium in a fully submerged position. It is in equilibrium in a fully submerged position. Okay, I think this is about pressure. What causes the upthrust? We know that upthrust is equal to cross-sectional area times difference in pressure. So difference in pressure between the top and the bottom of the submarine is responsible for the upthrust. So let's see, the air in the submarine is less dense than the seawater. The seawater exerts a greater upward force on the submarine than the weight of the steel. The submarine displaces its own volume of sea. The difference in water pressure acting on the top and on the bottom of the submarine. So the answer is D, difference in pressure on the top and bottom of the object. The ball is thrown vertically upwards. Neglecting air resistance, it means the acceleration due to gravity will be constant. Which statement is correct? The kinetic energy of the ball is greatest at the greatest height. Of course, at the greatest height, V is 0, so kinetic energy will be 0. That is not true. By the principle of conservation of energy, total energy of the ball is constant throughout the motion. This is very true. Total energy is going to be constant throughout the motion. So I think the answer is going to be B. Total energy is always conserved. It is always constant. However, loss in kinetic energy becomes gain in potential energy. By the principle of conservation of momentum, the momentum of the ball is constant throughout its motion. Momentum of the ball itself will not be constant. The potential energy, because at the highest point, remember V is 0, so the momentum will not be constant. The potential energy of the ball increases uniformly with the time during its ascent. Increases uniformly with the time during its ascent. Of course, if it is going upwards, yes, it is true potential energy increases, but does not increase uniformly because the speed decreases. So the gain in height, when it is getting to the highest point, is not the same gain in height when it was just leaving the lower level. So the answer is B. A cannon fires a cannonball with an initial speed v at an angle alpha to the horizontal. Which equation is correct for the maximum height h reached? Maximum height h reached. Which equation is correct for the maximum height reached? So we know that at maximum height velocity is 0, so that the highest point velocity is 0 in the vertical. So considering vertical motion, v in the vertical squared is equal to initial velocity in the vertical squared plus 2a in the vertical, s in the vertical. So final velocity in the vertical, at the highest point it is 0. Initial velocity in the vertical, we resolve this vertically upwards, and this will be v sine of alpha. So this will be v sine alpha. Because it is moving against gravity, acceleration is negative, so this will become minus 2 times g times the highest point h. So if I make h the subject, h is going to be, remember this is squared, h is going to be v sine alpha squared divided by 2g. V sine alpha squared divided by 2g, which makes the answer to be C. A goods train passes through a station at a steady speed of 10 meters per second. An express train is at rest at the station. The express train leaves the station with a uniform acceleration of 0.5 meters per second, just as the goods train goes past. Okay. Both trains move in the same direction on straight parallel tracks. How much time passes before the express train overtakes the goods train? Okay, let me begin with the goods train, because the goods train is moving at a steady speed. So the goods train, of course, they will have traveled for the same distance. In the same time, they will have traveled the same distance. By the time, how much time passes before the express train overtakes the goods train? How much time passes before the express train overtakes the goods train? So the distance traveled by the goods train S is going to be equal to time. This distance is speed times time. I will call that time t for the goods train. For the express train, the distance covered S is going to be ut plus a half at squared. By the time the other train catches up with the other one, they will have covered the same. It will have covered the same distance as the goods train. Or by the time The express train leaves the station with a uniform acceleration just as the goods train goes past. Okay, so as the goods train just goes past, the express train also starts. Both trains move in the same direction on a straight track. How much time passes before the express train overtakes the goods train? Okay, so by the time the one overtakes the other, they will have covered the same distance. Of course, they will have traveled for the same time. So S is going to be UT plus a half AT squared. So the distance is going to be 10T equals to, of course, the other one starts from 0, so initial velocity is 0. So this is going to be a half times its acceleration, which is 0.5, times the time squared, so times T squared. So 1T cancels. So we remain with only 1T, which is going to be 20 divided by 0.5. And I think this is 40 seconds. So the answer is going to be D. Which of the following is a statement of the principle of conservation of momentum? For an isolated system of interacting bodies, total momentum is always constant. So the answer is going to be D. The momentum of an isolated system is constant. A 2 kg mass traveling at 3 meters per second on a frictionless surface collides head-on with a stationary 1 kg mass. The masses stick together, so that means they move with a common velocity. Let's begin by conservation of momentum before we find how much kinetic energy is lost on impact. By conservation of momentum, total momentum before collision is going to be 2 mass times velocity, which is 3. The other one is at rest, so it is plus 0. Total momentum after collision, since they stick together, total mass will be 2 plus 1, which is 3, times the common velocity v. So the common velocity v is simply going to be 2 meters per second. So the velocity with which they move as a common body is 2 meters per second squared. So how much kinetic energy is lost? So the loss in kinetic energy, I'll just call it difference in energy, is going to be a half. For the first one, because there's only one which is moving, so I'll simply say a half times its mass, which is 2, times its speed, which is 3 squared. That's total kinetic energy before. Minus, after collision, it is a half. Total mass is 3 times velocity squared, which is going to be 2 squared. So this is 9 minus 6, which gives us 3. So the answer here is going to be D. A double-ended launching device fires 2 identical steel balls X and Y at exactly the same time. The diagram shows the initial velocities of the balls. They are both launched horizontally, but Y has a greater speed. Y has a greater speed. Which statement explains what an observer would see? Y has a greater speed. So both X and Y reach the ground simultaneously. They are both launched horizontally. So I think the answer is going to be B. Because they are launched both horizontally, the only force they have, of course, they are launched at the same time. So that means if we consider the time they hit the ground, I will simply use S equals to a half AT squared in the vertical. They will hit, because the vertical displacement is going to be the same for both balls, and the acceleration is the same for both balls. If air resistance is negligible, the time they will reach the ground is going to be the same. The time is depending on the vertical height, Sy, which is the same for both balls, and it is depending on the acceleration due to gravity, which is the same for both balls. So they will reach on the ground simultaneously. Both X and Y reach the ground simultaneously. Okay, so it means we ignore C and D, which are not talking about both reaching simultaneously. Then between A and B, the answer is B. The explanation for A is because air resistance will cause both to have the same final speed. For B, because gravitational acceleration is the same for both. So the answer is B. Gravity is the same for both. At time t equals to 0, a body moves from rest with a constant acceleration in a straight line. At time t, the body is distance s from its rest position. A graph is drawn of s against t squared, as shown. Which statement describes the acceleration of the body? So if we use s is equal to ut plus a half at squared, if at t equals 0, the body is at rest, so it means s is going to be a half times acceleration due to gravity g times t squared. If we plot s against t squared, it means that the gradient is going to be a half times g, which means g is going to be twice the gradient. G is twice the gradient. So which statement describes the acceleration of the body? It is equal to half the value of the gradient of the graph. That's not true. It is actually twice. It is equal to the value of the gradient of the graph. That is not true. It is equal to twice the value of the gradient of the graph. So the answer is going to be C. A lift elevator consists of a passenger car supported by a cable which runs over a light, frictionless pulley to a balancing weight. The balancing weight falls as the passenger car rises. So the acceleration of the balancing weight is downwards because it falls. The acceleration of the passenger car is upwards. Okay. Some masses are shown in the table. So what is the magnitude of the acceleration of the car when carrying just one passenger and when the pulley is free to rotate? So the passenger has a mass of 80 kilograms. So this side, remember Newton is second law, the resultant force F is going to be equal to mass times acceleration. So on the left hand side, we have the weight of the balancing weight, which is going to be 600 Newton, 640 times G, times acceleration due to gravity. Here we have the weight of the passenger, because one passenger whose weight is going to be 80. The passenger car is having 520 kilograms and the passenger is 80, so the sum is going to be 600 kilograms. So the weight here is going to be 600 times G. So on the left hand side, the resultant force is going to be 640 times G, or times acceleration due to gravity, minus the tension. Of course, there will be tension here. There will be tension here. So minus the tension is going to be equal to 640 times acceleration. The resultant force is mass times acceleration. So this is going to be the first equation. On the other side, on the right hand side, the tension is upwards. So the resultant force is going to be tension minus the weight downwards, which is 600 times G. So this is the resultant force is equal to the mass, which is 600 times acceleration A. When I say 600 G, it is 600 times acceleration due to gravity. So I'm going to say equation number 1 plus equation number 2. When I add the two equations, T disappears and I remain with 640 minus 600, then times G, which becomes 40 times G, which is 40 times 9.81. On the right hand side, I have 640 plus 600, which is 1240 times A. Okay, so here I got 640 G plus negative 600 and G, which gives me 40 times G. So the acceleration here is going to be equal to, I'll just press the calculator, 40 times 9.81 divided by 1240. So this is 0.32 meters per second squared. So the question is, what is the magnitude of the acceleration of the car when carrying just one passenger and when the pulley is free to rotate? So we are seeing that the answer is going to be 0.32. A stationary nucleus has nucleon number A. The nucleus decays by emitting a proton with speed v to form a new nucleus with speed u. It is, remember, initially stationary. So which equation gives the new nucleus and the proton move away from each other, so they move in opposite directions. Which equation gives v in terms of A and u? Okay, so the original mass, let me say the original mass is going to be A. A stationary nucleus has nucleon number A, so the original mass is going to be A. Mass is nucleon number times unified atomic mass unit. Remember, the nucleon number times unified atomic mass units gives you the mass in kilograms, so it is A times U. Where I want to distinguish this U here, let me make it capital U. A times U, where U is the unified atomic mass unit. Then the mass of a proton, we know that the mass of a proton is 1 U. The mass of a proton is 1 U. Okay, so the new mass now. The new mass is going to be the initial mass minus the mass of a proton. So that is going to be A U minus U. That is AU minus U, which is the same as A minus 1 times the unified atomic mass unit. Okay. So now, which equation gives V in terms of A and U? So the new mass is going to be A minus 1 times U. So let's use conservation of momentum now. By conservation of momentum, total momentum before is 0 because it was at rest. Total momentum after, it will be the new mass which remains, that is A minus 1 times the unified atomic mass unit, then times the speed of the new nucleus, which is going to be times smaller u, and then plus negative because they move in opposite directions. The proton has mass capital U times its speed. The speed of the proton is v. So the speed of the proton is v. So we want to find which equation gives v in terms of, so I make v the subject. So it means u times v is going to be A minus 1 into U, capital U, times small u. So capital U cancels out. So you notice that V is going to be A minus 1 into small u. A minus 1 into small u, which makes the answer to be B. Okay. So this brought in the concepts of particle physics anyway. So remember, 1u is 1.66 times 10 power minus 27 kilograms. That is 1 capital U, which is the unified atomic mass unit. A wooden block rests on a rough board. The end of the board is then raised until the block slides down the plane of the board at a constant velocity. That means acceleration is 0. Constant velocity. So the question is, which law describes the forces acting on the block when sliding with a constant velocity? Remember, acceleration is equal to 0, which means the resultant force should be 0. The acceleration is 0, the resultant force is going to be 0. So first of all, we ignore down the plane, the resultant force is 0. We ignore A and C. So of course, if it is sliding down the plane, if motion is down the plane, then that means friction is going to be upward, up the plane. So this is automatically friction acts to oppose motion. So the friction is going to be in the opposite direction, which is going to be up of the plane. So the answer is going to be D. A ball of mass m is thrown up to a height h in air with an initial velocity v as shown in the diagram. So this is our diagram. Air resistance is considered negligible. That means the acceleration is simply going to be g and constant. The acceleration of free fall is g. What is the total work done by the gravitational force on the ball during its flight from P to Q? So we know that work done is equal to force times displacement in the direction of the force. So the force, there is a gravitational force maybe, but then what is the distance? This is not weight, it is work. So work is going to be the gravitational force, which is the weight, or which is mg. This is going to be m times g, that is the gravitational force, m times g, times the displacement in the direction of the force, which is 0. Because if it moves upwards, it moves positive h. If it moves downwards, it moves negative h. Total displacement is going to be h, positive h plus negative h, which is equal to 0. So the work done here is going to be 0. So the answer is going to be A. This work done is force times displacement in the direction of the force, and the displacement is 0. So the answer is 0. One object moves directly from P to R. One object moves directly from P to R. In a short time, a second object moves from P to Q to R. So I'll use different colors. One moves from P to R directly, and in a short time another one moves from P to Q then to R, like this. Which statement about the two objects is correct for the journey from P to R? Okay, of course for P to R the displacement is just P to R, so the average speed, they have the same average speed, so average speed is total distance over total time, so this is not true. Total distance for PQR is not the same as PR. In a short time, a second object moves from P to Q to R. So they don't have the same average speed. They have the same average velocity. Of course, still they don't have the same average velocity because which statement about the two objects is correct for the journey from P to R? So if they take the same time, same average velocity, if they don't take the same time to move from P to R, then they also don't have the same average velocity. In a shorter time, because they say it is in a shorter time, average speed is equal to distance over time. Then average velocity is going to be displacement over time. But this is T1, this is T2, the time is not the same. So since T1 is not the same as T2, it means the average velocity is not the same as the average velocity is not the same for both because the time is not the same. So T1, if this takes T2, this takes T1. T1 and T2 are not the same. So even if this answer will be correct if T1 and T2 were the same, because the displacement will be the same for both. So the answer is going to be C. They have the same displacement. Since they have the same displacement, because displacement is the shortest distance between the starting point and the final point, so the displacement is the same. But since the time it takes for P to R is not the same time for PQR, then the average velocity is not the same, so the answer is C. The graph shows how velocity against time for a bungee jumper The graph shows how velocity v varies with the time for a bungee jumper. At which point is the bungee jumper momentarily at rest? Of course, if he's momentarily at rest, and at which point does she have zero acceleration? If he's momentarily at rest, v should be 0. That means r, this one here, v is 0, so it's momentarily at rest at r. So that means we ignore q, jumper at rest, that is at r, so ignore a and b. Momentarily at rest, v should be 0 at rest. Then she has, at which point does she have 0 acceleration? Remember, acceleration is equal to the gradient. Where is the gradient 0? The gradient is 0, that is at q. Here, gradient is 0. At the top, at maximum velocity, gradient is 0, the acceleration is 0. Gradient is 0, so acceleration is 0 at q. So at q, the acceleration is 0, so the answer is going to be C. Velocity is 0 when it is at rest. Acceleration is 0 when the velocity is maximum. An aeroplane travels at an average speed of 600 kilometers per hour on an outward flight and at 400 kilometers per hour on the return flight over the same distance. What is the average speed of the whole flight? Average speed of the whole flight. So for the average speed, we need total distance over total time. So we need the time first. We need the time. So let the distance be d. So time t1 is going to be equal to the distance d over the speed, which is 600. And time t2, when it is returning, it's the same distance d over the speed, which is 400 kilometers per hour. So the total time is going to be the sum of these two. Total time is going to be the sum of these two. So total time is going to be the sum of these two. So t is going to be equal to the sum of the two, that is d over 600 plus d over 400, which is going to be a d into that is going to be 1 over 600 plus 1 over 400. That is total time. So total distance, what is the average speed of the whole flight? So if it goes a distance d towards, so it returns back, so total distance is twice. So total distance is going to be twice d. Going d and returning d. So total distance is twice d. But the time to go is d over 600, the time to return is d over 400. Total distance is twice d. So we want average speed. So average speed is going to be total distance, which is twice d, divided by total time, which is d, into 1 over 600 plus 1 over 400. So d cancels out. D cancels out. So I remain with the 2 divided by 600 plus 400 divided by 600 times 400. I'm just trying to solve the 1 over 600 plus 1 over 400. So this gives me that would be 2 times 600 times that. I think that is 24. Then 1, 2, 3, 4 zeros. That is 24 and 4 zeros. So that is 240,000 divided by 600 plus 400. That is 1,000. So this gives us 4048. 3 zeros cancel out. So it is 480. So the answer here is going to be 480 kilometers per hour, which is C. What is meant by mass and by weight? Mass is the pool of, mass is the quantity of matter, or the property which that offer the property of a body to change in its, to offer resistance, to change in its motion, or to change in its acceleration. Then weight is the pull of gravity. So weight is the work done. That's not true. Weight is the property that resists acceleration. That's not true. Weight is mass divided by the acceleration of free fall. That would be true, but mass, coming this side, mass is momentum divided by velocity. That doesn't define momentum. Then mass is the force of gravity, which is not true. Mass is the pull of the earth, which is not true. So the answer is going to be D. Mass, the property that resists its acceleration, and weight is the pull of the earth on it. An astronaut of mass m is in space. In a spacecraft, experiences a gravitational force equals to mg. When stationary on the launch pad, what is the gravitational force on the astronaut when the spacecraft is launched vertically upwards with an acceleration of 0.2 g? So the F due to gravity is equal to m times g. So when it's launched upwards, the only force acting is the force due to gravity. Even though it's launched with an acceleration of 0.2 g, the only force acting is the force due to gravity, so the answer is still going to be mg. So the force, since it's launched vertically upwards with that acceleration, the only force acting, only force on it is gravitational force. So since the gravitational force is experienced when it's stationary is equal to mg, so even when it's launched, the only force acting is the force due to gravity. So what is the gravitational force remains the same, so it is going to still be mg. A beam of alpha particles collides with a lead sheet. Each alpha particle in the beam has a mass of 6.6 times 10 power minus 27 kilograms and a speed of 1.5 times 10 power 7 meters per second. A 5 times 10 power 4 alpha particle per second collides 5.0 times 10 power 4 alpha particles per second collide with an area of 1 centimeter squared of lead. Almost all of the alpha particles are absorbed by the lead so that they have zero speed after collision. So after collision, speed is zero. What is the estimate? What is the estimate of the average pressure exerted on the lead by the alpha particles? So first of all, we know that pressure is equal to force. Pressure is equal to force over area. And we also know that force is equal to the rate of change of momentum. This is small p for momentum. So pressure is going to be the force, which is the rate of change of momentum, divided by area times t. So change in momentum is mass times change in velocity, then divide by t over area. So this is, I'm just going to substitute here. The mass is 6.6 times 10 power minus 27 for each alpha particle. But how many are they? They are 5 times 10 power 4. So that is the total mass. Then the change in velocity, since they go to rest, so the change in velocity is going to simply be 1.5 times 10 power 7, of course, minus 0. Then divide by time. This is, the time is, of course, per second, so the time is 1 second. So I will say 1 second times the area. The area is 1.0 centimeters squared. I change it to meters squared, so that is times 10 power minus 4. Change it to meters squared. So I'll press my calculator, 6.6 exponent minus 27 times 5 exponent 4 times 1.5 exponent 7 divided by 1 exponent minus 4. So that is 4.95 times 10 power minus 11, or 5.0 times 10 power minus 11. So the answer is going to be C. This is 4.95 times 10 power minus 11. So the answer is going to be C. An object in air is thrown upwards and towards the left. It is thrown upwards and towards the left. Up, upwards, and towards the left. Okay. Which diagram shows the forces acting on the body when it is at its highest point? So of course, gravitational force acts downwards, force due to gravity is downwards. Because the object is thrown towards the left, object is towards the left, this is motion, is towards the left, it means air resistance must be towards the right. So this is the air resistance. So which diagram shows the forces acting on the body when it is at its highest position? So the answer is going to be D. The force due to gravity is downwards. So this is out. This ignores air resistance. Gravity is downwards, but since motion is to the left, air resistance is in the opposite direction to the motion, so that is to the right. So the answer is going to be D. The graph shows how the velocity of a firework rocket changes with time t. At which point on the graph does the rocket have the greatest acceleration? We know acceleration is equal to the gradient. And the gradient is maximum at B. So the answer is simply B. Acceleration is the gradient, and the gradient is maximum at B. So the answer is B. On a particular railway, a train driver applies the brakes of the train at a yellow signal, a distance 1 kilometer from a red signal where the train stops. The maximum deceleration of the train is 2.0.2 meters per second. Assuming uniform deceleration, what is the maximum safe speed of the train at the yellow signal? So we want initial speed at the yellow signal, which is something not very complex. So I'm simply going to use v squared equals to u squared plus 2as. At the red signal, the velocity should be 0. So 0 squared is equal to, at the yellow signal, the velocity is what we want, u squared. Since it is a deceleration, the acceleration is negative. So this will be minus 2 times 0.2, since it is a deceleration. Then times, the distance between them is 1 kilometer, which is 1,000. So I'll make you the subject just by multiplying 2 times 0.2 times 1,000, and I find the square root because u is squared, so the answer is 20. So it means u alone is going to be equal to 20 meters per second, so the answer is going to be B. A person traveling on a motorway at total distance 200 kilometers travels the first 90 kilometers at an average speed of 80 kilometers per hour. Which average speed must be obtained for the rest of the journey if the person is to reach the destination in a total time of 2 hours, 0 minutes? Now that's 2 hours. Okay. So total time should be 2 hours. But he first travels the first 90 kilometers at an average speed of 80 kilometers per hour. I think I should change the color of this pen. Okay, so let's first find the time it takes. First time t1, of course, time is distance divided by the speed. So the distance is 90 kilometers divided by the speed, which is 80. So it takes 9/8 hours for the first journey, and must take 2 hours for the rest of the journey. So the second journey, t2, is going to be 2 minus 9/8, which is, I think, 2, that is 18, 16 minus 9, which is 7. So this is 7/8 hours. For the second part of the journey, it takes 7/8 hours. So we want to find the average, which average speed must be obtained for the rest of the journey if the person is to reach the destination in a total time of 2 hours. So for the rest of the journey, the time it is going to take is 7/8 hours. And what is the distance here? The distance is going to be 200 over, so distance is going to be 200 minus 90, which is 110 kilometers. So the remaining journey is 110 kilometers, taking a time of 7/8 hours. So the average speed is going to be equal to 110 kilometers per hour divided by 7/8, which is 110 divided by 7/8. So that is 125 or 126 kilometers per hour. 126 kilometers per hour. So the answer is going to be D. A moving thorium nucleus, represented as that, spontaneously emits an alpha particle. The nucleus formed is radium nucleus, which is represented like that. Remember, initially we can assume that initially it was at rest. No, it was moving. A moving thorium nucleus, spontaneous emits. So it was moving in that direction. So it forms a new nucleus when it emits an alpha particle, and these ones move in opposite directions. Which statement is correct? Of course, in all collisions, total momentum is always conserved. So kinetic energy of the alpha particle equals kinetic energy of the radium nucleus. If they are equal, it means total kinetic energy is going to be kinetic energy of alpha particle equals kinetic energy of the radium nucleus. If they are both moving in opposite directions, that means each of them could be having a speed and their masses are not the same, so I don't think this is going to be possible. Then the momentum of the alpha particle equals the momentum of the radium nucleus. This is also may not also be correct in magnitude. This may not be correct because if they are equal, it means total momentum is not going to actually be conserved because they will cancel out each other. Total momentum before the emission equals to the total momentum after the emission. So the answer is going to be C. By conservation of momentum, total momentum is always going to be conserved. This is always conserved. Total momentum before the emission should be equal to total momentum after the emission. So the answer is C. However, B would be correct if the thorium was initially stationary. But if it is moving and after collision the others move in opposite directions, then it means momentum is not conserved. An isolated system consists of two bodies on which no external forces act. The two bodies collide with each other and stick together, so they move with a common velocity. Which law correctly compares the total kinetic energy and total momentum of the bodies before and after collision? So P, total momentum, is always conserved. Momentum is always conserved. Momentum is always conserved, so let's check. Total momentum before and after collision, it should be the same. It is always conserved. But then the two bodies collide and stick together. That means final velocity is going to, the relative speed of separation is 0 because they stick together. There is no difference in their speed. So since they stick together, total kinetic energy is not conserved. So it must be different. So we ignore one which says the same, and the answer is going to be B. Total kinetic energy will be different because they stick together, but the total momentum is always conserved. Lastly, in part 12, a mass accelerates uniformly when the resultant force acting on it is 0. Sorry, you have to choose one of those. A mass accelerates uniformly, that is uniform acceleration, What is this? Sorry about that. So uniform acceleration. A mass accelerates uniformly when the resultant force acting on it is uniform, because force is equal to mass times acceleration. If acceleration is constant, the resultant force should also be constant and not zero, because it is accelerating uniformly. So there is an acceleration which is not zero. So it can't be, the resultant force can't be zero because they are directly proportional. So zero is wrong. Then B is constant but not zero, because uniform acceleration means constant acceleration. So it means the force should also be constant but should not be zero. So the answer is going to be B. The answer is B. I think I should change the battery. So the answer is going to be B. So I think that marks the end of part 12. And I hope you have learned something. In case of any problem, any mistake, I'm always bound to make a few errors here and there. So you can always write to me and I try to correct the errors. Until next time, bye bye.